Hello and welcome to my final group project for advanced electronics. I'm going to go over the whole circuit first, and this is for a solar powered robot that uses basically a capacitor bank for its energy source and not a battery. And basically, by using a dedicated 4.95 regulated rail and a unregulated rail, it's able to manage the energy in such a way that it can move a specified distance as specified by the given pulse width modulation it receives through a NMOS FET, two of those, one controlling the current flow and one controlling the pulse width modulation. To start off with, we start off with a solar panel here, and we modeled that with 0, 500, and 1000, which is the difference. These numbers correspond to different uh, values of ambient light. Then we had a constant we feed in here, which is 25 is room temperature, and then 45 represents a hot, you know, like a hot panel in direct sunlight. And then those values then are placed in this. They're calculated in here and then placed over here based upon data sheets. Then I added this block here to convert between Simuscape Electrical to Simulink. And then once I did that, I compared both sides to make sure that the power entering from one type of system, Simuscape Electrical, was the same as Simulink. Oh wow, oops, sorry. Simulink. And then I went on my merry way. And then what I did, I added, it was a Zener diode here and a Schottky's diode. One regulates the voltage potential right here so that it doesn't harm the capacitor bank. And basically, if it goes over 5 point, uh, if it goes up to like 5.6, 5.7, 5.8, if it gets up that point, then it basically will feed off that voltage down to ground, and that protects our capacitors from seeing too much voltage across them. And the Schottky diode protects is in reverse bias to actually protect the panel from the discharges that are in these capacitors. I put a switch here to isolate my solar panel from my capacitor bank during when I have the robot turned off. I start off with one capacitor in here, a 1 farad capacitor. It wasn't enough, so I added another one. That still wasn't enough. And so later I added a 10 farad after realizing that's how much I needed. It's around 12 farads for a good 4 second to 63-second run. It averaged that I needed about 12 to do that. And depending on good or bad conditions, it can be up to only 4 seconds. It depends upon the torque needed to move, the elevation that the robot's on, what pitch it's at, or friction or other concerns. If it's most ideal conditions, then it can go for quite a ways, though. So all that is the reason why I chose that specific value. Continuing on, that's where I get this 5.5 here. Basically, is just subtract the voltage drop from the the Schottky diode here from what you're getting from your photovoltaic solar panels. Then it comes to that value, so it doesn't charge over its regulated amounts here. Uh, so basically, once you finish that, then I added a bleeder resistor so that when the circuit is powered off, it will discharge and won't stay charged to harm someone or keep basically just to protect people from handling and getting shocked. So basically, it slowly dissipates eventually. And I set it at 4.3 specifically because that was the time constant that I wanted. It came to be like a 1.2 days or something, but then I added more capacitance, and I don't know if I changed this or I did. I think I changed it once, but I didn't bother changing a second time. This one value I may need to go and revisit again, but I think that it's still it balanced between energy loss during when the during when it's running and when it's powered down. That's why I didn't want to go over that amount. I mean, under that amount, because if you get lower, then it starts, just sending the power stored right to ground, which doesn't do anybody good. So you need a balance between the two. Up here, all this stuff is monitoring my different input and output bus power from basically input is one side and the output's over here. Even though it's sharing the same node with the capacitors, the influx of current versus the outflux of current, there will be an actual difference between the two. And this allows me to see when the capacitors are actually charged by monitoring that. So that's that part. If we drop down here, we're going to look at our full regulated rail, which I found out I needed this later. So this powers my ICs, resistors, capacitors, anything that goes through sensing logic and not power straight to the motors is powered by this regulator rail. It can go down to like I think 1.2 or 2.1, something like that, and then it goes all the way up to like 5 to 6. So basically, it keeps outputting this value, and it just goes and draws more current to maintain this value when it gets lower, and then it'll bleed off the excess if it goes well over this. And that's why it's called buck boost, because it either bucks what it's given or it boosts what's given. So that's why I had to get that. I couldn't use a straight buck or a straight boost because I need to have, since I have an unregulated rail that's constantly charging and discharging and everything, I needed to get something that would be able to regulate from both extremes. Basically, I modeled it using this DC-DC converter in Simulink, and I went ahead uh, and mapped all this stuff on the actual. I see how I would connect it so I would know where the values go. And that's why sometimes the behavior doesn't run exactly as I want. And there's issues because I can't throw this in there because I don't have all the capacitors and stuff of what's inside here. I got a second switch here. The first one I told you before was to isolate my panel from my capacitor bank to protect both. Uh, this is to protect all the rest of my circuit downstream from the regulated in case I want to shut it off. And that's what that's for. It's just a single throw, single pull switch. Then goes into my 555 timer. This is the astable oscillator. Yet has multiple variable resistors, which I changed from 100K to 250 to have more range up here. And I I connect some of the wipers to the legs, and sometimes I use the whole range between one side, depending on the application. And the way this works is the path of the if you as you vary the resistance, the length of time that the capacitors down here discharge corresponds to the length of resistance that it has to go through. So if you want it to have a shorter time period, then you want less resistance. If you have more resistance, it's going to take a longer time constant. And this allows you to adjust your duty cycle, whereas this resistor up here, variable resistor, allows you to adjust mostly your frequency. And these capacitors right here are pure frequency adjustment. This is pure duty cycle adjustments, and this is a hybrid of frequency and a little bit of duty cycle adjustment. And all these values here I chose after lots of calculations, kept trying them until I got the range that I wanted. My center frequency, I wanted 2000K, so that's where all this comes from, is me getting to make sure I could get it right where I wanted it. So if there's discrepancies, that I would be kind of where I want. So if it goes one way or the other, I would have wiggle room to adjust it, the rest of the circuit. This is my astable oscillator. I can't wire this here, but we have this pin from 1 to 8 for decoupling that we doing in the regular circuit. We go on, these protects the gates of the MOSFET right here. And then this one here, the resistor helps pull the gate to ground when there isn't a signal. So it keeps at 0. And then I linked up the motor, both motors, the left and right, I linked together. And basically this one 555 and one gate powers both of them. And I model all those stuff in here. And I put a snubber in here, which is this capacitor and resistor. And then I used a flyback diode over here to protect from voltage spikes. This is another softener. This basically softens this, and this protects it from the spikes on the motor from if it stalls. Same thing with the other one. So that covers that section. Then what I did over here was I did a bunch of first I did angular velocity, acceleration, and position in here. And then I converted that over into instantaneous linear velocity, acceleration, and position, so I could see how far the robot was going based upon my pulse width modulation chosen. And my duty cycles from that, which would determine how far it goes, based upon power, and my and the thresholds determine when. Um, So basically, it's determined how, when, where. Basically, everything is all those questions are addressed by different components of the robot. Here we have pulse width modulation adjustment. Like I was telling you before, this is my frequency, this is my pulse width modulation, and this is my trimming for my uh, frequency. I use those to trim to get closer to the frequency I want. And then what I also did was I have this up here, which is our other MOSFET. This controls the current flow through it, whereas the other one controls the pulse width modulation. They work in tandem. This basically works as a electronic switch, which is occurring over here. This is the pseudo version of the electronic switch, and I monitored, as you can see, that when it's switched, these numbers will equal each other. And when the switch is not engaged, this value here turns to 0. So the motors are actually no longer connected with a capacitor bank, and the capacitor bank has a chance to charge, so it can be used again. Without this, and then all the power just keeps bleeding off of the motor, and nothing ever happens. So that's why this is critical that the second MOSFET had to be added here, and I couldn't just use one for pulse width modulation. I needed to have a second one that's controlling like a clamp, shutting and opening when the motors receive and when they don't receive power at all, or or current basically in volts from the pulse width modulation is controlling volts. So anyway, so then I built these two equivalent circuits up here. These are the actual chips that you put in the circuit, not modeled. That's just so I know where all the connections are going. And I changed these as I worked on my started with 100. I ended up going with 250. And I've calculated where I wanted to set my thresholds using this voltage divider here, which I use for both the light sense and the energy sense sides. And what else? Okay, that's good. And then I modeled the comparators using both Simulink and Simuscape electrical. That's why I have it repeated twice, because some ports of the system would only accept one version or the other. So behind here, I'm using one version, and through here, I'm using a Boolean. One's using a Boolean logic, and one is using voltage levels. The voltage levels were the only one that Simulink or Simuscape electrical would only accept one, and one would only accept true and false statements. So I end up using both. And that concludes the overview of the entire circuit, which is pretty quick. And now we're going to look at some signals. We'll run it for a second here. We are, as you can see, if we adjust this potentiometer, the duty cycle changes, but the frequency doesn't. If we go and change this one, which is the frequency modulation, the frequency changes, but just the duty cycle changes a very little bit. Like I was saying, it's this is a hybrid, but very little duty cycle, but mostly frequency. And if you move these, you have difference in difference in frequency without any difference in pulse width modulation or duty cycle. And then this one, same thing. This one's of course, and one of them is rough adjustments. So that's that information. If you look at the overall power, it plots it in here. I don't have that much working now, but this is basically the bus and then the solar coming in. Um, if you have if you want to look at the pulse width modulation, this is not pulse width modulation yet because it hasn't built up enough charge. This is just leakage. So this is the leakage that's occurring even with everything shut off, or if the comparator and the light are actually on, then it's just passing straight through it. And we can look at that real quick. And I wanted to show you one thing real quick over here. This is this would be showing you how far the robot's going, but it actually hasn't gone anywhere yet. This is really basically zero, but this still takes mathematical value, so it'll still plot something, but it's actually not really moving at all. But if when we had charge stored up in the robot and the conditions were true, then this would show you the distance, the acceleration, and the velocity of the robot itself. And then you could look at the pulse width and pulse width modulation and all. And then by adjusting the two, you could actually have the robot go 5 feet, 3 inches, whatever you wanted to go. And it would correspond to that based upon the thresholds that you set and from the comparators and the pulse width modulation, how fast, how you wanted that to go to the robot itself. All right, and then so if we look at this, one other thing we'll look at really quick is, what was the other thing? Oh yeah, we'll look at this, which is just if you shut these and open these, if you reduce the thresholds here, the energy thresholds been met, say the light has thresholds been met. If you see here, see everything is passing through. If one of them, if you think the energy is no longer good, then immediately this shuts off again here. See, there's no current going through here, and there's almost no voltage. So basically it's zero right now. So nothing is passing through here right now at all. And you can see the volts also, how it's not going through at all. And if we plot this, if we were to plot the switches turning on and off, it would actually plot here the signal being switched on and off. It shows that switch being shut on and off right here. This top part is where it's on, and this is when the switch is being closed, the electronic switch is being closed. And that is also, I have a display here so you can actively see when the switch is being shut off and on right there as well. So you don't have to keep opening the scope. And I did the same thing, that all these are connected together. So when you adjust these potentiometers here, it actually adjusts the one in here. I've linked these together, and I've also linked a lot of other things all over the place together, because I'm using a lot of gauges and stuff from the simulation to be able to go and control this stuff easier and more intuitively. But I also I want to show you, I used a math block in here, and this is outside the code. So let me show you this really quick. If you click on this, there's a little bit of code here that basically pulled in the values from my gain and everything else here. And I basically did some blocks and whatnot, and I figured out these gain ratios and stuff. I've calculated that, so I wouldn't have to do a bunch of math. I'd figure out specifically a gain, and then I would go and use that gain. Like this is the 250K resistor. And based on that, you can go and calculate the stuff by adjusting the gauges, the a percentage of where this is at. It'll take a percentage of this, and then it passes it through all this stuff, and then sums up. It took about a day or 2 day, a day and a half to design all this, just the calculations alone. But that's everything. Also, you can also, when I first started building the circuit, I used these switches over here to look at behavior because I can shut off the switch manually. I mean, switch off the circuit manually, or I can use digital. But now that the circuit is finished and designed, I rely on the electrical switches mostly, and I only use these switches if I was wanting to power off the robot for storage. And that concludes my demonstration. I would have liked to go a little bit more in depth with it, but I have been sick with a really bad flu all week, and I am exhausted because I've been up for 2 days. But enough about me. I hope you enjoyed this project. And you can see it does run, it does work. It has a little bit of bugs with it, but all my stuff and all my resistors, capacitors, inductors, and everything else. And yes, there is one inductor that I used on the voltage regulator, the DC-DC buck boost. He does use one inductor right here, a 10 microhenry right here, for bleeding off and transferring that voltage and current over. Uh, so basically, that concludes our project, and I hope you enjoyed. I hope you have time to read and look at all this. I hope I went slow enough so you could follow. And if you have any questions, of course, leave them in the comments. And I will try next time to be a little bit more awake. But thank you again. And this is my project that I'm going to try to probably going to make into a capstone project. And this is just my getting my feet wet, my toes wet, so to speak, in through robotics and seeing if I want to go that route. I really did enjoy it. There were some days I never thought I'd get done with it, but I was happy to see that I did actually get it done. And I learned a lot more in this than I did the entire semester taking the actual advanced electronic course because it pushed me beyond that. There's your error. It takes quite a long time, but as you can see, there are errors, but like I said, there are errors that I have not worked out yet, and it's actually caused by the actual blocks not wanting to communicate with each other. And to resolve that, I'll have to either model more, like I was saying, model the actual ICs themselves more on a component based, is get rid of those errors, or keep the power section separate, and work on them. The problem is I was wanting to see the whole thing working together, but just like it's the more parts, the more things can go wrong. But it does work, and I'm happy with how it turned out. And I thank you again, once again, for watching, and I'll see you on the next one. And thank you for your time.